Hello, my name is Christopher Nichols, and I'm going to be going over the final project for ADTA 5340. Okay, so the first part of the final project was a strategy to employ machine learning in the firm. So my company is ChemScope Data Solutions, is a mid-sized publicly listed company that provides chemical data services to government agencies as well as small and large private companies. The company currently has 50 employees that include analysts with extensive scientific backgrounds, as well as a small team of data engineers that maintain several small-scale databases for each sub-discipline of chemistry. So, for example, biochemistry, geochemistry, and industrial chemistry. The scope of the company's services includes applications in industrial chemical operations, pharmaceutical research, geological surveys, and biomedical testing. So such applications include spectroscopic analysis, pollution detection, protein gene sequencing, and soil nutrient assays. So our competitors will be Databricks, Dedico, Palantir Foundry for energy, Schlumberger's Delphi platform, and Thermo Fisher's AI analytics tools. So these companies are already using several types of machine learning models, such as deep learning neural networks, to win lucrative government and private industry contracts. So to remain competitive, we need to deliver faster and higher quality analytical services in addition to our domain knowledge. So we need to expand offerings using advanced machine learning applications. So such as deep learning models for chemical spectroscopy interpretation, machine learning based petrological or rock composition analysis, regression models for predicting outcomes of chemical sample analysis, convolutional neural networks for fossil identification and species classification, and to provide engineering firms and government agencies with predictive models for forecasting research and development expenditures. And we need to leverage a combination of our strong suit, which is expert human domain knowledge with chemistry and in its subfields with modern machine learning tools. So to increase operational efficiency and reduce costs and to strengthen ChemScope's differentiation from competitors, it will be beneficial to employ extensive machine learning. So we were going to propose using the ecosystem that includes Google Cloud Platform, Big Lake, Apache Hadoop Spark for storing and processing large volumes of data, our clients' data. We're going to have BigQuery for data set manipulation, fast querying, and extracting valuable analytical insights, and Kubernetes to manage and deploy microservices and ongoing machine learning subprojects. With our deep learning frameworks, we want to employ TensorFlow, Keras, and PyTorch for image classification and spectroscopic deep learning workflows. And then we would want to also emphasize the use of MLflow to track multiple machine learning experiments, manage models, and organize project development. And Google Vertex AI to optimize model hyperparameters, manage workflows, and streamline end-to-end data and model pipelines. So to implement this in our hiring, we want to find 5 data scientists, 3 machine learning engineers, 2 data architects, 3 data engineers, and 1 cloud engineer. And preferably, we want to find these that have special knowledge. Because remember, in our company, we want data uh, experts. We want domain experts, sorry. And we want chemical engineers, geochemistry experts, and biomedical engineering if we can find those people that happen to have this extensive machine learning, data science, and AI expertise. We want to fund for our current staff machine learning boot camps and professional development programs for current employees with deep scientific expertise. We want to hire 3 machine learning trainers, educators to conduct regular internal training sessions, and also provide tuition assistance for select senior and tenured employees pursuing further studying AI and machine learning. Okay, let's get to part 2 about data pre-processing with the animal shelter data set. We see that we have over 95,000 records of different pets or animals that have been put into the shelter, and their outcome type will be what the outcome type was. Was it an adoption? Was there a return to owner? Or was there euthanasia? So we removed unneeded columns. So I went ahead, took out animal ID and the date of birth column, since that will not be important for predicting outcomes. And I also took out the month year because that would be redundant because we already have a column called date time. And speaking of date time, what I went ahead and did was I formatted date time using the to date time method so I can extract the month from that and convert that month to a numerical value of either 0, 1, 2, or 3. I then map those numbers to the names of the seasons and create a new season column and drop the date time column entirely. So I did this because some seasons may see increased animal adoption rates, especially during the spring or winter seasons compared to the fall. I then dropped the daytime column altogether for a more condensed data frame. And then I converted the age upon outcome column to age in months by creating a function that converted string variables that are in the age upon outcome into numerical ages in months. And I applied that function to the age upon outcome column. So this first one, I'm pretty much illustrating through code what was discussed in the last slide. I put every value in the date time column through to date time. I was able to extract the month from that and take the modulus with 12, then divided that by 3, and that would give me a season. That would be either 0, 1, 2, or 3. So then what I did was I took season and mapped it using this map dictionary I used here, and that gives me a new column that gives me winter, spring, summer, fall, and I took out the daytime axis. Now to create the age and months data, what I did was I made a function that takes in a string. So the string is stripped and everything's made lowercase. If it happened to be a null value in there, I return nothing, or nothing was in that, or there was nothing in that at all, whatever the case was. However, if the string had years in it, then I still did the same thing where it was the string was split, and I took the first value that was in the string, which would be the number usually. And I took that number and multiplied by 12 to give months, and it gives me an integer of value. And if it was month inside the string, then I took the number and converted to an integer that gives me months. I applied this function to age upon outcome. I have a new column that says age in months. I dropped age upon outcome. Then I simply dropped any NA values. And this is my new clean data table. It has the animal type, sex upon outcome, breed, color, outcome type, which is our target, but the new column season and age in months is shown here on the right. So then I also want to go ahead and clean up any records that had a 0. And when I did that, I ended up with a few hundred less records. Okay, and so that was cleaned. And so for part 3, I'm going to use the abalone data, which is a type of like shelled organism. And I was going to predict the age of the abalone using a random forest model. And as you can see here, you see weight of several sorts, height, length, diameter, and sex to help predict the number of rings, which will be used to predict the age of the organism. The only variable here that's not a number will be sex. So what I went ahead and did was I took out any 0 values first, and then dropped any ENAs, and there's not much. I think there was only like 2 records that were dropped after that. I mapped males as 0, females as 1, or indeterminate sex as 2. And after EDA with the histograms, we see that the rings has a much narrower distribution than the rest of the predictor variables. The same thing can be seen with the density plots. So since there's such wider plots for our predictor variables, that gives the possibility that you will have a whole lot of different organisms, different records that have different characteristics, but they all end up having around the same value as their target variable. Also, there's lots of outliers with the ring target variable as well, and with the other variables, as I should note as well as too. When we do our scatter plot matrix, we see there's a lot of high correlations between the several predictor variables. The whole weight is very correlated with other different types of weight. The length is very highly correlated with the weights and the diameter as well, and with the height. And so that gives us lots of multicollinearity. I also want to make a heat map to show how much these variables are highly correlated as well. Most of the variables, when you put them through the heat map, have a value of 0.8, which is very high correlation. The only one that's not highly correlated is sex. So with that evidence, I've assumed that a linear regression model may have trouble with so many collinear variables and outliers. And also, since we have those outliers and that tremendous amount of skewing in the rings data, I took the log of the rings to see if that would help the model out. And so, due to all this, I chose the random forest model to be the best. And it was also important to keep in mind the sex predictor variable might not be very helpful for a linear regression model, but for using it in a categorical manner for the decision trees in the random forest, that might be a better decision. So with the random forest, I set up set it up to contain 1,000 independent decision trees, and each tree had a depth of 20. It was done to make predictions more stable and reasonably complex. The minimum number of samples a tree could have before it splits was set to 10, and that could help the model avoid too much overfitting. And minimum samples per leaf were set to 6 to buffer against overfitting as well. I made my arrays. I did not include the ring column, but I did include the log of the rings as my target Y array, and all the other predictor variables were included, excluding the rings. And then I made the test size be 0.33%, well, 33% with a seed of 7 using the train test split function. So when I evaluated the model using the R squared value, I only got a 0.626. And when I evaluated with k-fold cross-validation, I used the negative mean squared error. And I got, with that, negative 0.029. So even when scaling the data and using a large random forest model, the accuracy was still only moderately high, a little bit above half. And this seems to be since many different individual abalones with different measures have the same number of rings, and there are lots of outliers. And that presents a lot of noisy data. So therefore, very accurate predictions using this data set are hard to produce. So on the plus side, the negative mean squared value errors were very low, meaning predictions were consistent against multiple training testing sets. So for the two new records used for predictions, I chose numbers around the mean values of the predictor variables, and the model predicted values within the range where most of the target variable values were, which was between 8 and 12. So, but in order to get the age, though, you have to make sure to add 1.5 to the exponential of your prediction because we took the log. So we reversed that with the exponential, got the rings, and then added 1.5 to get the age. And they all fell within that predicted range. Okay, so for part 4, we're going to do K nearest neighbors with the adult salary data. So our target variable is going to be the income, and we're going to look and see if this person is going to have an income mainly possibly above or equal to 50,000 K or less than 50,000 K. And we see we have a mixture of categorical and numerical values. So first thing I did was I dropped the FNLWGT column. And then I need to remove these question marks. So however, and I want to replace them with NAN so I could drop those. However, after trying to use the replace method to replace the question marks with NAN, the question marks still remain, as you can see at the bottom left here. So I had to play around, and what worked out the best was adding some spaces before and after the question mark. It's still using the replace method, and that seemed to do the trick of replacing the question marks with NaN, and then I simply dropped my NAs. Now, when you look at this coding right here, you may be wondering why I am making a copy of my column values here. That's simply because for some reason the notebook was having trouble keeping up with which data frame I was using, especially after um, rename, not saying DF3 equals DF3 drop NA. So what I went ahead and did, it seemed to work well if I just made a copy of the data frame, and it was able to streamline better. Okay, so then when I look at my target variables, I see that I have these extra periods right here, and it makes the variables redundant. So what I ahead and did was I did the replace function again and replaced the period with just a space there, and that reduced my target variables to either less than or equal to 50,000 K or greater than 50,000 K. And I want you to notice the imbalance here. There's more than three times the amount of less than or equal to 50,000 K than more than 50,000 K. Okay, I converted all the categorical variables to numerical after that using the PD categorical method. We can see that most of the records are people below the age of 50 from a histogram and density plots. Capital gain and capital load values are very heavily skewed to the leftmost extremes. They include zeros, so I didn't want to take out those zeros. That would just only leave a couple of records left in the data set. So zero seems to be a very important consideration as a predictor for this. There was also lots of outliers uh, based on um, based on these box plots. And again, we need to keep in mind that we had that large uh, variable imbalance for the target variable. There does not seem to be much correlation between many of the variables in our data frame. And because of that, I went ahead and chose the k nearest neighbors model since KNN does not assume linear behavior in the data. And there's not too many variables, and there's not too many different types of predictor variables that we're using, so that's not going to slow it down too much. So when I set my number of neighbors for k nearest neighbors, I set it at 4. That seemed to do the best because when due to that imbalance in the outcomes, the higher the neighbors seem to hurt the accuracy because higher neighbors allowed for the majority class to drown out that minority class if the scope of the prediction was allowed to be larger than 4. Okay, then I split my data frame into X and Y arrays with the income to be the Y array. I set the test size to 33%, a seed of 7, used train test split as usual. And when I used the classification report, the model did a great job with less than or greater equal to 50,000 K. However, it struggled with greater than or less than, less than, excuse me, the model struggled with somewhat with a greater than 50,000 K because we had scores below 70 for that. And that's going to be mainly due to that class imbalance. However, we did have respectable accuracy of 83% and a K-fold cross-validation accuracy of 84%, just using accuracy with that. The predictions that I made, the new records I made, both predicted less than or equal to 50,000 K, which would make sense because most of our records were that. And since the model did really well with that type of outcome, the output, the F1 score was much higher for less than or equal to 50,000 K. That could probably be safe that those predictions are accurate. Okay, moving on, we're going to do K-means clustering with the car evaluation data set. We see that with this data set, we have these price, maintenance, doors, passengers, luggage, safety as a predictor variables, and evaluation would probably be the target variable. Um, Before performing EDA and splitting the data, I checked for zero and NA values, which there were none. And I ordinal encoded the categorical values using a map method and set numbers for each type of for low, medium, high, very high, since most of those variables had that type of scheme. And this is the data frame you see below right here, where it's those numbers instead of the strings. So from the plots shown below, we see that there is very even distribution of the different types of predictor variables here. And if we look at the evaluation, we see that it skews toward unacceptable to the extent it's nearly 3 times as large as the next largest value acceptable. So the vast majority of our cars here were deemed unacceptable. And so it seems like we might see that even though they might have different predictor variables, different other characteristics, they might all point to the same target. And then from our scatter plot, there's not really a strong correlation between any of the two variables as well after ordinal encoding. And then from this heat map and these mosaic charts, there's not high correlation according to the heat map with any of the variables. The highest is 0.44, which is not too terribly high. And if I were to look at the prevalence of each type of the predictor variable when it's compared to the other, you just see this even split. The only time you don't see the even split is when you put any of the predictor variables against evaluation. And for each time we look at the evaluation, unacceptable is associated with each one of the different types of prices. For the most part, these are the bigger chunks or spacings for unacceptable there. So, like I was saying, different predictor rows, different rows, even though they're very different from each other, will point to the same outcome. So this might give clustering trouble. So for this unsupervised model, I'm using k-means clustering because I use that ordinal encoding for the Euclidean distances. And we want to not use the evaluation in this as well. So we would use k-means clustering. So I put my number of clusters as 4. So even though I'm not using evaluation, I'm not running it through the model, I still know there's 4 different variables of values for evaluation. And I print out my centroids and the labels that were produced. And when I try to make a 2D plot, we only see small group of evenly spaced dots. And as you can see on the right here, I messed with the chart here, the plotting, to make artificial noise so that I could separate each data point. And we just see clusters, but they're all evenly spaced and they're evenly mixed together. There's no clear demarcations between the different types of colors that you have here. So when the cluster centroids are plotted, the centers are well off from the data points, as you'll see in the next slide. And so as predicted from the heat maps and the mosaic charts, the model is having trouble making good clusters since there's not really any strong relationships between the predictor variables and no close groupings could be made. So it's just very important to point out there's a severe class imbalance that may hamper the model's ability to see good patterns and make good separations. So even if I did not include the evaluation in there, there's still not much like patterns that you can find here. The unacceptable target value is only 70% of the total outcomes, and several records with very different predictor variables seem to have the same output. I said again. So the ordinal encoding doesn't seem to have given the model ability to calculate meaningful Euclidean distances for clear separations. So the predictions made by the model for the 2 new inputted records should not be viewed with much certainty, as you see below. Okay, so we're moving on to comparing regression models using a chemistry data set, and we're going to predict something called Gibbs energy. And just for some background, the Gibbs energy of a molecule is used to determine if the chemical reactions that that molecule may be involved with will be favorable. So we're going to select a certain amount of these columns here to try to predict this G298. So that means the Gibbs energy at room temperature, pretty much. All right. So the variables I chose were the HOMO and LUMO, which are the energies of different molecular orbital levels. The gap refers to the energy difference between the HOMO and LUMO. And the alpha and mu columns refer to characteristics that describe how easily electrons can be pushed to one side of a molecule or polarized. And the number num atoms refers to the number of atoms in a molecule. Okay. So as usual, I dropped any zero or NaN values from the data set, and the discussed predictor variables were selected. So I took out anything that wasn't discussed. And so this is my data frame I used. And there was several, and when you'll see in the EDA, we can see that we will see that there were several outliers in the target variable. And so from that, I decided to take the log of the Gibbs energy as well. And took out the columns I didn't need. So here's the box plot I took that shows all the different outliers that were found. And I decided to take the log of the Gibbs energy because of that. So from the scatter plots, we see positive correlations between LUMO and HOMO and the gap. So LUMO and HOMO had a positive correlation and negative correlation between the HOMO and the gap. And that makes sense because the higher the energy level goes up or down, the wider the gap between the two levels will be. So we're seeing that. Okay, so the first model used was a simple linear regression model that was trained on 67% of the data, 33% used for testing. I tested the linear regression model on just the first 2,000 records because those were smaller molecules. And then I did it on the whole data set that included the larger molecules to see if there was a difference in the performance. I did the same with a very basic decision tree with the same basic breakdown between training and testing sets. And with the decision tree, the best results came when the max tree depth was set at 15 and the minimum number of samples needed for a split was 5. Okay, so as we can see with the regression, at first with the first 2,000 records, the R squared value was decent, 0.896, but when I included the whole data set here at the bottom, the regression struggled greatly. The R squared value was only 0.296. The decision tree did pretty respectable at the beginning too with 2,000 records at 0.887, and it stayed more stable after the whole data set, even though it did drop, it was at 0.810. For both models and for the different data set sample sizes, the predictions on the new record remained relatively the same. For all predictions made, the value remained around 6 kilojoules per mole. It hovers around that. When I did k-fold cross-validation, um, what we see here is some pretty good values for that. It was very low. All of them were about 0.003. So since the decision tree model's R-squared value was relatively high and the tenfold cross-validation scores were very low at 0.003, the decision tree model can be considered at least moderately reliable in predicting the Gibbs energy of a molecule compared to a linear regression. So that seemed to be the best model for that. Okay, so now let's compare a categorical model of models of logistic regression versus k-nearest neighbors. So the data set used for this exercise was the Kingdom Codon data set, and this data set contains over 13,000 records and contains features that describe the species of an organism, the kingdom that the organism belongs to, the number of three-letter DNA sequences called codons, and the codon frequencies for all the different combinations of codons. So the kingdom of the organism belongs to is considered the target variable. So I dropped our any record that had NA in first. Then I checked the number of target variables values. There were several target values that were extremely small compared to the others and made up only a small fraction of the total data set. Therefore, I eliminated those target values that were under 600. I did this to avoid any problems that class imbalance may bring to the classification model. So I dropped the NaN values and I checked, and there's 0 for that. So since the DNA is double-stranded, and one strand has the opposite codon of the other, you would have a redundancy in your column variables, your predictor variables. So I reduced the amount of column variables even more by using principal component analysis, and it lumps very correlated column values into a single feature, thus reducing the amount of noise in the data. And I set the number of components produced down to 30, which is almost half the original 66. So from the histogram that I produced here, we can see that several of the codon histograms have different scales. And since we need a single standard codon frequency, I standardized the predictor variables using standard scalar as well. And so I used the basic logistic regression model first, again, with 67% training, 33% testing. I fit the PCA and standard scale data directly into the model, did the same for k-nearest neighbors classifier. So used the same amount of data for each training and testing. And the best results for K&N were gained by 5 nearest neighbors. So as you can see, both did relatively well, with most of the values being above 70 for logistic regression here on the left. You can tell by I named them all logistic regression. However, there's a few that were around that 0.54, 0.56 for some of the classes here for recall and F1 score, but those values were higher using the K nearest neighbors. And there's the lowest here that you see for any of the classes was 0.77. The accuracy for K nearest neighbors was also 93%. When a new record was put in both models predicted the specimen belonged to the plant kingdom. Due to the high accuracy and classification of the reported values for both models, especially the K&N model, this seems to be reasonable. When the tenfold cross-validation using accuracy was measured, the logistic regression model scored 85%, and the K&N model scored 93%. Both models had high accuracies for all folds. So based on the results of accuracy, classification report, and tenfold cross-validation, the K&N model did the best job in predicting the kingdom an organism belongs to based on codon sequences and the number given. With such a high evaluation score, predictions made by the K&N should be taken confidently. And that is my presentation. Thank you.